Once you know your area and you have determined your velocity, you can easily calculate the flow rate to be equal to AV. But remember, we have already defined that V is equal to KI. So it means that in the absence of V, if I have KI, I can still calculate for what? My flow rate. And that is why the formula, the V is taken off, and now you have this, which is this. So then let's move on. So the coefficient of permeability, which I said is the K we have computed earlier, or it is also termed as the hydraulic conductivity of a material. So knowing this has the dimension of length per unit time and decreases as the particle size decreases. Why are we saying it decreases as particle size decreases? It decreases as particle size decreases because when particles are of larger surface area, what happens? They provide, when you pack them, they provide a lot of empty spaces around for the flow of material, of water. But as particle sizes decreases, they fill in all other empty spaces because they have a smaller surface area. So they are more dense when you pack them. And so that will decrease the flow rate. And that is why this statement is there. And then an estimate of the actual velocity. So now, this velocity we have calculated is an average velocity based on the assumption that the water is flowing without any distraction or obstruction. So we term that an average velocity, the V we have calculated earlier. Then we have the actual velocity that will occur in the soil sample or your rock sample, which is actually in natural sense what we've been dealing with, because you don't have water flowing unless surface water, runoff water. But then the actual flow of water through our rock medium is termed as what? Seepage. So to determine the more or less the speed of that flow, we term that the seepage velocity. So seepage velocity is talking about the actual flow through the soil medium, the speed of flow through the soil medium. And so to determine that, then now we want to multiply our area, which we know already, times the seepage velocity itself, rather than using the entire velocity or the average velocity, which we assumed that the water or the fluid is flowing without obstruction. Then we have said that before flow in a fluid can occur, it occurs through the interconnected pore spaces, which means there is something called porosity which is coming to play, and then the void ratio, which is more or less a measure of you trying to find out the percentage or the amount of empty spaces to the solid you have, the entire volume you have gotten. You are finding a ratio of the empty spaces to the entire volume of material you have gotten, of a substance you have. And so we have the seepage velocity expressed as the average velocity over your porosity. And so, and this porosity can be expressed in form of what? This one, which is what we term as the void ratio. And so once you know this expression, then we can play with this small question and see whether the understanding is there. So it says that the flow rate from a soil of cross-sectional area. So you see, because we may be asked to calculate quantity of water, the flow rate, they are telling us the area So now the area of whatever soil sample is determined as 2,500 millimeters per millimeter square. And then the flow rate, which is the Q, is given to us as 0.05 times 10 to the power 6 per second. The head difference, so the head difference is talking about the change in elevation from reference A to reference B, where the water is flowing. So the head difference has been given as what? Over a length. So the L is also given as 300. Then the head difference is given as 60 meters. They are telling us to determine the hydraulic gradient, the average velocity, the seepage velocity, if we are given void ratio, and then the hydraulic conductivity, K, or in other words, the permeability, the coefficient of permeability. So step 1, we are to find the hydraulic gradient. So to find hydraulic gradient, which is I, we only need the change in H over the L. And the L was given as 300. The change in H is given as 60. So you have 0.2. Remember, it is unitless. Then determine the average velocity. Average velocity is determined as what? You need the flow rate is equal to the area times the average velocity. Don't mind that Z there. The Z there is only telling you the direction of flow. You know, a flow occurs in a given direction. So in this direction, we are being told that the flow is in the Z direction. If you draw a Cartesian plane, okay, where you have your X, Y, and Z. And so they are telling us the direction of flow. That is why the Z is there. So now, our area is given as 2,500. We have our Q given. So the only thing missing now is the V, which they say we should find. So you make it a subject of this expression. And then you have 2 times 10 to the power minus 5 meters per second. And that is the velocity, average. So we are being told to compute the seepage velocity. To determine your seepage velocity, that one you need the average velocity divided by your porosity. But remember, we were not given porosity in the question. Rather, we were given void ratio. And void ratio and porosity have a relationship, which we saw earlier. And so that relationship is this. And so now we have this value, which is our porosity. So now we can come back to this expression and work out our seepage velocity. Then the next thing is for us to determine the hydraulic conductivity, which is the main thing the geotechnical officer will be looking for to see, or the dewatering team in your mind will want to know about the material. And that is always the velocity is equal to your Ki. And so now you know your average velocity, you know your gradient from the initial computation. So you can only make this the subject of the equation. And that gives you this. So it means you should expect a flow roughly of what? 1 times 10 to the power 1 centimeters per second. And that is your permeability constant. Having been able to know this, then how does groundwater affect us? So the water pressure in any given rock material or soil material, one can affect the stability of slopes by diminishing the shear strength. So we explained that shear strength is more or less about the rock's ability to resist sliding. And so once you put that, if there is the presence of water, it reduces that particular strength by way of serving as a glue, a fluid in a way, some kind of a smooth oily surface that will make slippery easy. And so that is what the role our material is going to play. That is, if there is water in our rock or in our soil, it reduces this shear strength, and at the end of the day, that shear strength is such that it can no longer support slopes, because when you have slope, one point is higher than the other, and it's expected that this shear strength should be strong or high enough to avoid sliding. Then we have changes in moisture content of the rock. So changes in moisture content of some rocks, particularly the shale, can cause accelerated weathering. So if there is that quantity of water, moisture in our rock sample, it facilitates weathering, which will reduce the durability of your rock sample. Then freezing. Freezing is a situation where you have water within your rock sample and then you have this cold weather condition. It freezes, and then once it freezes, it reduces the strength of the rock because it can crack. It can cause crack within the sample and then cause a lot of wedge failures when you least expect them. Then erosion can set in once your water is not causing, it's not damp but flowing. Erosion can easily occur. Then it can increase your excavation cost, because when working below the water table, for example, wet blast holes require the use of what? Water resistant explosives that are more expensive than non-water resistance. And also the flow of groundwater into the excavation or the pits sometimes require dewatering, which is all at a cost to management.